can start. Good morning, everyone. It's our pleasure to start this session today. Our invited speaker in this session is Professor Antonio Facchetti. He's the co-founder and the chief technology office of Poleria Corporation. He obtained his PhD chemical sciences from the University of Milan, Italy, and carried out postdoctoral research at the University of California, Berkeley, at the Northwestern University, where he currently is an adjunct professor of chemistry. Professor Facchetti has published about 275 research articles and 7 book chapters and holds about 60 patents. He received the 2009 Italian Chemical Society Research Prize, the team IDT Tech EX Printed Electronics Europe 2010 Award, and he is a 2010 Cavelli Fellow, a 2012 American Association for Advancement of Science AAAS Fellow, and a 2013 Materials Research Society MRS Fellow. He was selected among the top 100 materials scientists of the past decade, 2000-2010, by the Thomson Reuters. He is the founder and editor-in-chief of Organic Photovoltaics and associate editor in the International Journal of Analytical Chemistry, and serves in the editorial advisory board of Journal of Applied Polymer Science. Professor Facchetti research interests include organic semiconductors and dielectric for thin film transistors, conducting polymers, molecular electronics, organic second and third order nonlinear optical materials, and organic photovoltaics.
Thank you. Great. Thank you again. Thanks for the invitation. I'm going to try to summarize some of the work we've done on developing materials for a few different optoelectronic devices, mostly looking at printing some of these devices. The devices I've been trying to summarize are mostly based on devices which are organic thin film transistors, and I'm going to show you some example of materials we have developed and what are the key challenges in enabling the printing of these materials. Also, we are trying to make flexible transistor based on metal oxides, and there is different methods to develop mechanically flexible oxide, and one of the approaches we have recently developed is mixing metal oxide with polymer to enable amorphous phases. And the last part is try to make organic solar cell here, a bulk heterojunction solar cell, using, again, material which can be mechanically flexible and could be printed. I'm going to start very briefly about talking about Poleria Corporation, because this is my primary affiliation. I'm an adjunct professor at Northwestern, but my primary job is a Poleria. And the company was started 10 years ago in 2005. We are mostly a material company which enable material for some of these technologies. We have 3 sites, one in Skokie where we do chemistry, one in Taiwan we do process engineering, and one in San Francisco where we do actually design, and we have about 100 employees. And the things we are trying to make are some of these electronic components which can be integrated into mobile, wearable, and very simple circuits to drive very simple sensor elements for Internet of Things. So very simple technology. One of the other things we are trying to do is make display, to make the material which can then be integrated into display, which can be then bended and flexed. And here the key challenge is to enable a multi-stack technology which can be robust enough to not only enable the flexibility of the stack, but also the mechanical impact in the everyday usage. So this is quite a key challenge. So the key components to make the device I show you is the organic transistor, and the TFT is a very simple device. It's a 3-terminal device where you have a source, drain, and gate. These are the contact. You have a semiconductor, and you have the dielectrics. And the way the device works is you have a very low carrier density in this interface. So although you apply a bias, and there is no bias between source and gate, there is no carrier. So in this current voltage plot, you are in the off states. But by applying a bias to the gate, you induce carrier at the interface. So you have carrier, you have bias, or you have current. So you can switch this device on and off by changing the polarity of this potential. And depending on the nature of the carrier, if they are p-type holes, you have p-type semiconductor. If you have electron, you have n-type semiconductors. And the key parameter is the field effect mobility. But I don't have time to enter into detail. But what is the key issue? The key point is if you are trying to make mechanically flexible display or elements, all the material in the stack have to be mechanically flexible. So you need to be enabled, the whole stack, which has to be robust enough to survive this mechanical stress. At the same time, if you want to make this device by printing, all the materials have to be printable. So the whole infrastructure has to come together at the same time. And we've done quite a few amount of work with collaborators. Some of them are highlighted here in red, in doing chemistry, mostly looking at chemistry of the semiconductor and the dielectric, and also looking at phenomena affecting charge injection and transport at the interface. We use silicon as a model, but there is a uniqueness in terms of how charges move in these devices, in these materials. And also looking at the effect of the interface and charge trapping at the interface due to the dielectric, due to chemical reasonings. In terms of molecular design, we have, these are going back to the origin, we develop a number of families. You can see here these are quite different in terms of functionality and structure, but we have developed a number of molecular semiconductors which for this technology. I don't have time to enter into the details, but one of the key characteristics of this material is they conduct electrons quite efficiently. It was a sort of one of the major bottlenecks of the technology at the beginning, and we're talking about mid-2000. The other things we have tried to do is to not only to make good conductors, but this conductor which can be printable. And this is an example of a typical protocol that we do. We use plastic, metallized plastics, which we usually cut. And then we take our molecule. This is an example of cyanated perilene diimide, which we can formulate. And then this is a very simple process. This is called inkjet printing, like you print your paper, your documents, and then you have these drops which lands on your substrates, and you need to worry about the topology of the drops, how they merge together. So there is a lot of work we do in this aspect. We also develop polymers. Polymers, if you think about mechanical stress, these could be more suitable. And we develop polymer as a dielectric. These are some families we have developed. And we have done a fair amount of work on developing polymer, which are semiconductors, which can be based on these ditieno-imide structures. Again, there is this imide functionality combined with this mix electron-rich, electron-poor heterocycle, using this new type of alkoxy functionality directly on the double bonds, which provides unique, very poor very poor electron density increase in the core. We are looking at the sort of pi neutral type of functionalities. And I'm sorry about this, it's very hard to see, but we develop n-type polymer. This is a sort of our horse, a battle horse in terms of material we have developed for transistors. But why we are interested in polymers, let me skip this. We have done actually work to try to develop inkjet printable polymeric formulation, and what you usually end up with something which looks like that. Because of the rheological property of the polymer, basically it's very difficult to eject it. So we've done actually quite amount of chemistry in trying to get to optimize the polymer architecture, and usually by changing the end functionality or changing the molecular weights to enable inkjet printable polymer, semiconducting polymer for these applications. Another way to print is called gravure printer, and this is very different. It's not like a drop which is ejected on your substrate. You have a sort of cups, and these cups you just like a cake, and you just dump on your substrate, and then they melt together, and they get close. So using this particular polymer, which we developed a few years back as an N-type conducting polymer, we could make, by tuning the viscosity of the solution, get film which are uniform enough, thin enough, continuous enough to make quite nice field effect device fabricated by gravure printing, which is more mass producible technique. Using this polymer has been quite used in the community to make not only transistors, but also been making circuits, vertical transistor, all polymer solar cell, more recent, because of the electrochemical activity, making also batteries for lithium-ion batteries. So it's a polymer which has been quite interesting to us. So we did some chemistry to try to make it reproducible and to try to scale it up. And if you look at, if you are organic chemist, this is a very quite simple synthetic route until you get to this type of reaction which provides the polymer. This is a polycondensation, which is metal catalyzed, but the problem is you have a distannyl functionality. And having the units in such a way, this chemistry runs smoothly and produce the same quality of polymer. We had to do a fair amount of work in optimizing the stoichiometry, the catalyst, the reaction times, the conditions. But we have been able to scale up this chemistry from a few grams to a quarter of a kilo, maintaining the very good control in terms of molecular weights and for transistor performance, also in a very similar range in terms of transistor performance. So it's a chemistry that can be scaled up for those of you who are interested in organic synthesis. What is the problem is when you do this chemistry? The problem is, actually, I would say about 90% of the cost is to dispose the byproducts. And the most dangerous byproduct is trimethyltene bromide or trimethyltene hydroxide, which is produced in the chemistry and is present in a stoichiometric amount. So it's an environmental concern, but it's also actually a real issue. So we try to develop chemistries which do not need to have this functionality here, but starting with a building block and using zinc as a sort of organometallic intermediates to form the polymer, which is the same as the one which we achieve using Stille type of chemistry. And to make the story very short, we can achieve comparable molecular weights and comparable field effect mobility. So this is an alternative route to make this polymer. We can use in this type of approach, we use nickel as a catalyst. Nickel is not as active as palladium, and when we use palladium, we can tune the molecular weight in a very large range to make it much larger molecular weight if we want. So by tuning this, we can transfer the printing process from a very small scale gravure printer to a much larger printer where the semiconductor, but also the dielectric, the electrical contact have been printed. And we can make circuits. This is just to give you a little flavor of what we do. Another effective way to print is it doesn't pattern, but it prints. It's called a slot die coating or bar coating. And the uniqueness of bar coating is that if you especially for polymer you have your high molecular weight macromolecules, and a slot die coating or bar coating is a sort of sliding technique. So you can think about these rods, these polymers gets aligned during the printing. So the question is, can we take advantage of the alignment because of the printing methodology to achieve higher performance compared to other techniques such as which are typically spin coating. And this cartoon shows that we can print with this technology. These are the electrical contact in the direction of the electrical contact, which means perpendicular to the charge transport. Charge transport is in this direction, or we can print in this way where the electrical contacts are here. So it tells you that we are printing in the direction parallel to the charge transport. And the results are quite impressive, as if you basically print in this parallel mode, we can achieve mobility which are much larger compared to the perpendicular mode. And this is really because these macromolecules gets oriented. And we spent actually spent quite some time to really understand what is the degree of alignment and where the alignment is confined, because you can think about the film thickness. Where do these macromolecules are aligned? Is at the surface? Is the bulk? Is it the bottom interface? So using a variety of technique, we could understand that the alignment is preferentially at the surface, and what is preferential, and this polymer which are aligned is where the charges gets confined and gets transported. This is what this work has told us. So let me switch to another class of materials. They're still in the vision of printed electronics, which are the metal oxide. And metal oxide are a sort of competitor to organic, and the reason is because metal oxide compared to silicon type of semiconductor, they can exhibit very high charge carrier mobility also for amorphous phases. So for silicon, you have to have crystalline phases to get very high carrier mobility. When you go to amorphous silicon, the mobility drops 3 orders of magnitude. But for metal oxide, the difference in mobility between single crystal and amorphous phases is a few factors. Factor of 1, a factor of 2, very, very little. And the reason is because for metal oxide, the transport is, the conduction band is S metal orbital based. So no matter if you have a perfect lattice or if you have a distorted lattice, this orbital, spherical orbital, provides a good path for electrons. Okay, so this is why it's very important in terms of a vision of printing the electronics. Also, metal oxide can be optically transparent, so they can have also other advantages. And people have been looking at this material in conventional electronics to, for example, in this TFT, you actually see the stripes, right? You see the single pixel because the amorphous silicon is optically opaque. And this take away some of the light from the back of the display. So you have what is called aspect ratio, which suffers because the silicon is opaque. But if your TFT would be transparent, you would save a lot of energy because this light goes through. So this is one of the applications of metal oxide. The other area is making invisible displays, and a third area is flexible electronics, is because of these amorphous phases are mechanically tolerant to mechanical stress. This is not important. So we have done a fair amount of work to deposit metal oxide going from vapor phase, from solution phase using preformed nanostructure, or using Sol-Gel methodology and other methodology. But what is the key importance, especially if you think in the vision of printed electronics and flexible electronics, is you really need to make an amorphous phase. So what is the typical way to make amorphous phase in a metal oxide? The more conventional approach is you start from a matrix, which could be indium based, for example, indium oxide, or zinc based, zinc oxide, and then you start adding elements. So you add gallium, you add a little bit of zinc, a little bit of tin, and when you have more elements because of the difference in the geometrical dimension and the coordination chemistry, the lattice gets confused, so you get amorphous phases much more effectively. So this is the typical way to make amorphous phase. And we have shown some results on this. A new way which recently discovered, is actually to take your matrix, which is in this particular case indium oxide, and then we use an insulating polymer, which is soluble into the metal oxide, And the question is, we are doping this matrix with an insulating polymer. So the question is, can this metal polymer be creating amorphous phase? What is the microstructure of the film? What is the charge transport capability? How do they change? So there is a few questions we had to answer. The first one is, these are X-ray scattering experiment. This is the matrix, indium oxide, which is polycrystalline. And then these are different doping level in weight of PVP, polyvinyl phenol. 1% you still have a little bit residual crystallinity, but then the phase becomes completely amorphous, okay? So, and this is dependent of the processing temperature. This is a little lower temperature, this is a little higher temperature. But so we can get amorphous phases. Obviously, upon addition of PVP, the film remain optically transparent. This is not so important. We try really to understand at the molecular scale, so what do this polymer do? Because you can think about, you can form a solid solution, or in metal oxide you have typically these octahedral which are connected, and having a good connectivity is where the electron then can move through, okay? So if you want to have a material which can remain a semiconductor, it means these octahedral have to be somehow remain connecting upon doping with the polymer. And this experiment using X-ray absorption fine structure tell us that we do disrupt the lattice of the matrix to some extent, but this octahedral remain connected, and we can really see by looking this coordination number, this coordination length of the second sphere. So we still have this octahedral which mostly through the edge of this octahedral remain connected, which is essential to have some degree of transport. And then we started making devices to make, make the story very short. Yeah, let's look at this data. Here is the field effect mobility, and this is with the percentage of doping with the insulating polymer. The red is the mobility, and you see that the mobility does drop when we start adding the polymer, but there is a sort of regime which is on the order of between 1 and 5%, where the mobility remains quite large. The threshold voltage, which is also another important parameter, remains very close to 0, which is very good as well. And the mobility remains, and the processing temperature is acceptable. So there is really a regime where we get amorphous phases characterized with quite decent electron mobility. And here are mobility on the order of 2, okay? Maybe I skip this important parameter. The field effect mobility for the transistor using this display, which are based on amorphous silicon, the mobility is on the order of 0.5. So having a mobility on the order of 1, 2 is significant. It's not good to make, chips to driver as a driver, but they are sufficient to make to drive liquid crystal display or other type of simple displays. So this is definitely a new way to create these amorphous phases. And then we have done mechanical bend experiments. And if you use the matrix alone, which is polycrystalline, and you start bending, it's a little difficult to see, but you start forming cracking into your film. And this cracking results in a dramatic decrease of this current voltage plots of the current because of crack formation and propagation. Instead, when you start doping with this insulating polymer, because of the amorphous nature, the variation of the mobility is much, much more contained. Okay, so it's quite new, interesting way to make amorphous phases using metal oxide. The last part, I want to talk a little bit about some of the work we've been doing on solar cell. And I don't know, I didn't expect to have this, but for those of you which are a little less familiar, the ideal process, I don't know if it's going to work, that we took is just simply to start with a plastic which can be then coated by your bulk heterojunction photoactive layer on a simple roll. And then when this is already, the coating has occurred, and then it goes into the heating systems, and then it should come out, is to start drying, and then eventually will dry completely. This is a simply P3HT based blend which should come out purple to a certain point after it's completely dried. Okay, so the process is very, very simple. If you look at in the vision of printed electronics, this process is at the current stage of the technologies really can be industrialized, because the process is very simple, could be tolerable to small amount of particle. This is completely not tolerable to particles. You have 1 pixel dead over 1 million and your display do not work. Here, if you have a particle, it doesn't really matter. The panel will continue to live unless you have shortage. So in terms of the printing methodology and the possibility to do something is far easier than having printed backplane. So it's a technology we have been interested in. And the stack in this type of devices is very simple. You have your photoactive layer, which is sandwiched between the two electrodes, and you have some interlayers typically to promote the charge extraction. Okay, and we've done a little bit of work in this area, looking at chemistry and looking at, again, charge extraction. One of the things we have done recently is looking at some of the interfacial layer, and one of the interfacial layer that we have been looking quite extensively are for inverted architecture to try replace, for example, zinc oxide with metal oxide, which can have a much more tunable energetics at the interface. And this is very important because until a few years back, we have only PCBM as an acceptor. The energetics variation of the acceptor were very, very small, but now we have much more variety of acceptors. We have small molecule, we have polymers, so we really need to expand the variability of this energetic variation of the energy at this interface to be really more close to the variation in the energy of your acceptor. And we have done this again using metal oxide and using doping to change the energetics of this interfaces by really quite a large amount. You know, we can go from about 3.5 to about 4.3, 4.4 electron volts. So quite tuning in the energetics. We also done quite some work on developing the molecular, the photoactive layer, both looking at the donor semiconductor. These are some of the small molecule we have developed a few years back, very, very simple systems. More recently looking at more donor acceptor system as expected. They work better in terms of efficiency. And also looking at polymer donor. We look at, for example, this borazine type of structure, this thiazole, this more extended DPP type of structure based on pyrazine, heterocycle, and this which is we call isomeric DPP, where we switch the nitrogen and the carbonyl to make a different heterocycle compared to the conventional DPP. And these are some of the efficiency we have reported. One of the systems which is we have been working more extensively as a donor unit are this imide type of functionality. And when you design a donor polymer for OPV, it's a little more tricky than when you design a whole conductor for transistor. When you look at the transistor, you are only looking at the energetics and the transport. When you're looking as a donor in a bulk heterojunction, you look at the transport, but you look at also at the energetics and the position of the HOMO to optimize the VOC and the mixing also of the polymer is something which is quite tricky to achieve. Achieving the morphology is quite more difficult. The right morphology is more difficult. So this type of unit, they were quite suitable, and this is a very old work, as of 2013. But we have shown when we use this imide functionality copolymerized with a 3T type of unit, we could achieve a decent efficiency for the time between 7 and 8%. But the field factor were very, very large, very unusual, I say, for the time. And we try to rationalize the high field factor because of the uniqueness in the morphology, where you have your acceptor with zinc at the bottom, very nice face-on orientation of the blue parts of the stack, of the polymer, and the right phase separation. So having a combination of phase gradation, phase separation, and the right morphology of the polymer was a sort of the right recipe, which we did not invent. It was discovered. It just happened. There was nothing to invent. So it was a good morphology. It has a huge drawback. If you take this blend and you heat it up at 120 degrees for 5 minutes, the efficiency and the fill factor drops about 50–60%. So it's not a very stable morphology. So we tried to develop a chemistry which could stabilize the morphology. And one of the ways we did it is using, for those of you who are organic chemists, this azide functionality. And we wanted to use this azide functionality, but having a chemistry which will not form nitrine. We don't want to form nitrine, but we want to have a chemistry which goes through the formation of aziridines type of chemistry. It's something which we could achieve using this type of cross-linker. And when we start cross-linking, you take a certain blend and you start warming it up, you have this huge phase separation. So the efficiency of this cell decreases dramatically. When you start cross-linking the blend, the efficiency remains of this cell are much more stable. So this is one of the approaches we have done to try to stabilize the morphology. Let me skip this. We have also worked on try to make, this is mostly done at Polyera. Obviously, it's important to achieve high efficiency in single cell. What is more critical is to achieve decent efficiency, and here we are talking about 80% at the module level, where the bulk heterojunction blend is deposited not in the glove box, but is deposited in air. So it is given, it is accepted that we must encapsulate the cell. But what is essential is that the cells are produced in ambient condition, and not all the equipment has to be under nitrogen. And this blend can achieve quite decent efficiency, as I said, about 8% upon deposition in ambient. And this is the cell upon light soaking. Right now we are more than 3 years. This is a little older, and the retention of the efficiency is on the order of 90%. Okay. The very last few minutes, I want to talk, one of the work we have done more recently is really try to move away from a P3HT or donor acceptor based on a fullerene, but using a blend where both the donor and the acceptor are polymeric. And this is something which remains challenging, not in terms of, it's not challenging from the theoretical point of view. I mean, there is really no difference. I mean, why this blend should not work as well as fullerene? There is really nothing fundamentally different. But what is the real key problem is to achieve a morphology which is comparable in terms of domain size and domain purity as in certain region as the polymer fullerene type of cell. So we started actually this project way back in 2008, 2009. At that time, we used as a combination, as a donor and acceptor, one of the best donor at the time, P3HT, and one of the best acceptor at the time, which was this naphthalene diimide type of polymer. We put it together, and the initial efficiency were on the order of 10 to the minus 3, so quite low. We're starting to understanding better how to process this cell, and this is a sort of the best we could come. And here it really tells you that this is the schematic of the blends of this polymer as a function of the type of solvent you are using to process them. If you use a solvent such as dichlorobenzene, you have a complete stratification. You have the N-type polymer, it goes on top of the blend. The P-type polymer is at the bottom. So if you look at the PC of these blends are in red, is very, very poor. The field effect mobility is good because you have transport in this direction, okay? So you have phase separation is great. But in the diode direction, you have only very small interface, so the PC is very, very low. The diode mobility are very, very low, and you have good field effect mobility. When you start using better solvent, which mix the two polymer a little better, the field effect mobility drops, the diode's mobility picks up, and the efficiency starts increasing. So we went from 10 to the minus 3 on the order of 1%, just by changing the processing a little bit. What we also discovered more recently is that if you have two polymers, if you have a polymer, the donor and your fullerene, it's really no matter how the two domains get together, right? Because fullerene is spherical, and it really doesn't matter how they get close. But if you have two rods, the way they get together is very different, whether they get together at the interface like this or they get together like this. And it's very important. This is something you need to worry about when you make polymer-polymer blends, how these two domains get together. And this is the work done by, I would say, completed by the group of Dr. Neher, using some of our polymers, really having a continuity at the interface between the donor and acceptor polymeric domains is very important to really enable the splitting of the excitons. More recently, we found a little better combination by using, again, as a polymeric acceptor, this naphthalene diimide polymer. This is it was a new polymer developed at University of Hong Kong. And when we use this polymer, we create domains, we create blends where the domain size is not optimal. We're still quite large, it's on the order of 100 nanometer. So it's not as small as we want. But this film remains quite crystalline upon blending. And we can start getting efficiency, optimized efficiency on the order of 5%, which are still far behind from what we know for fullerenes, but they're starting becoming more interesting. We have done more work using polymer blends. This is mostly done at Polyera. We had it certified polymer blend, I think on the order of 6.5. Right now we are a little over 7% with using polymer, which I cannot disclose now. But just to give a message that we are slowly but getting very close in terms of efficiency. There's really nothing preventing the technology to achieve the efficiency of polymer fullerene cells. We are just a little less behind, but we are getting closer. So with this one, I conclude. I hope I give you a little flavor about some of the work we've done on organic transistor, making this flexible display. I think we are there. We've been looking at metal oxide for transistor application, but also for solar cell as an interfacial layer. And I gave you a flavor a little bit about some of the work on solar cell, on developing some of the materials and cross-linking chemistry, and a little bit about polymer blends. And with this one, I conclude. I acknowledge most of the people by the papers that I've shown at the bottom. These are some of the collaborators and some of the funding agency. And with this one, I thank you for your acceptance.
Thank you very much also, Katie, for this amazing lecture. And we have time now for 2-3 questions from the audience.
I have a question about the stuff. You said that particles will not affect the printed organic cell, but if you get a particle, you will get short and the cell will be destroyed. This is the normal understanding.
Yeah. Maybe I didn't explain me completely. In terms of sensitivity to particulates, these displays are much more sensitive than a printed solar cell. I mean, to make this display, you have to be in class 100, and the whole process flow has to be done under that conditions. For solar cell, if your panel, when you coat the photoactive layer, you are in the region which is about 1,000, also a little higher than that. If your formulation had been filtered correctly, you can make very decent panels. So the defectivity due to particle is not as dramatic as in the case of displays. That was what I meant. but you need to control the particle. You don't have to, yeah, a particle, if it creates a shortage, is a problem, but the particle per se could be acceptable.
Okay, excellent talk. But you think you can disclose some of these ink solvents which you are preparing, or it's still company know-how?
Yeah, the type of solvent I cannot disclose it, but the solvents have to be strictly regulated. There's differences between Europe, which is the most strict, and Japan versus other countries which are a little more forgiving. But for sure, they do not tolerate chlorinated solvents. They do not tolerate iodinated additives.
Boiling point, can you just
The boiling point is, it has lost the flash point is, is acceptable. Boiling point is not as critical for the process, but is critical for the formulation. If the boiling point is too low, then typically you start forming particulates in your ink because of the surface evaporation. So the solvents that for the cell we use in real products, all the solvents are not chlorinated and they are not halogenated, and they are not restricted in the using the OSHA type of protocols.
Thank you.
Yeah, you're welcome.
Further questions here? From the female section, do we have some questions? If no, so very
Thank you.
greatly thankful for you and for this amazing lecture and for accepting our invitation. Thank you again.
Yeah, delete it.
Session will be presented by Dr. Sher Bahadur Khan. He's an associate professor at the Center of Excellence for Advanced Material Research and Chemistry Department, Faculty of Science, King Abdulaziz University, in Saudi Arabia. The title of his talk will be Cobalt-based nanomaterials as facilitating electrocatalyst in electrochemical waters.
Okay, I will do it. No, I will do it this one. Okay. I can change from them. It's okay. Bismillah ar-Rahman ar-Rahim. I would like to talk about cobalt-based nanomaterials as a fascinating electrocatalyst in electrochemical water splitting. As we all are hearing about the energy crisis on daily basis, and whenever we hear about the energy crisis, our minds start thinking that might be the price of fossil fuel has been increased that are responsible for the energy crisis. But we are not thinking or unaware about the depletion of the fossil fuel, because we are at the peak of oil age. At the same time, our newspaper highlighting on daily basis about the global warming and environmental pollution. There are many things which contributing in the environmental pollution. One of them is the continuous combustion of fossil fuel. The continuous combustion of fossil fuel give big threat to the environmental pollution, and it is one of the serious issue that should be solved. On the other hand, the energy demand is increasing day by day, and the global energy demand for the sustainable development would be almost double by 2050. So, the searching for green and renewable energy is an urgent task. Many efforts are going for the green and renewable source development that should be clean, free of carbon, cheap, and should be viable alternate of fossil fuel. There are many energy resources which are considered as renewable energy, such as geothermal, wind power, hydrothermal. One of them is hydrogen, which has got much attention as a next generation carrier because of its minimal impact on the environment. And similarly, it has also some other characteristic property which make it unique as compared to the other renewable energy resources. The importance of the hydrogen energy is clear from the interest of different companies. And according to the manager of Dutch Shell, that we are at the peak of the oil age, but the beginning of the hydrogen age. Anything else is an interim solution. This transition will be very messy and will take many technological paths, but the future will be hydrogen economy. Similarly, the director of the General Motors says that the General Motors absolutely sees the long-term stability. Similarly, the General Motors absolutely sees the long-term future of the world being based on hydrogen economy.
Respected sir, we can hear you from the starting. Can you start it from the beginning?
Okay, Bismillah.
Okay, thank you so much
Welcome.
for your cooperation. Thank you so much.
The topic of my presentation is cobalt-based nanomaterial as a fascinating electrocatalyst in electrochemical water splitting. As we all are hearing about the energy crisis, and whenever we hear about the energy crisis, our mind start thinking, or we are thinking about the price of the fossil fuel, that only the price can make the crisis of the energy. But we are not thinking, or we are not aware about the depletion of the fossil fuel. The reason is we are at the peak of the oil age. But it is fact that there is continuous depletion of the fossil fuel. Similarly, we are hearing our newspaper highlighting on daily basis about the environmental problem as well as the global warming. So many things contributing and making environmental pollution. One of them is continuous combustion of the fossil fuel. The combustion of the fossil fuel make a big threat to the environment, and that should be solved. On the other hand, the energy demand is increasing day by day, and the global energy demand will be almost double by 2050 for the sustainable development. Thus, the searching for green and renewable energy is among the urgent tasks. Many efforts are going for searching the green and renewable energy resource. This green energy resource should be cheap, clean, free of carbon, and should be viable alternate of the fossil fuel. There are many type of energy resources which are considered as renewable energy, such as geothermal, solar energy, hydropower, but among them hydrogen energy has got much attention because as a carrier of next generation because of its minimal impact on the environment. There are also so many properties of hydrogen energy which make it unique as compared to the other energy resources, and the importance of the hydrogen energy is clear from the interest of the different companies which consider hydrogen as a future economy. According to the Dutch Shell manager, that we are at the peak of the oil age, but the beginning of the hydrogen age. Anything else is an interim solution. the transition will be very messy and will take many technological paths, but the future will be hydrogen fuel cell. General Motors director says that the General Motors absolutely sees the long-term future of the world being based on hydrogen economy. There are different ways by which hydrogen can be produced, such as thermolysis, electrolysis, biomass conversion, and photolysis, and so on. There are so many different methods, but among this, the electrolysis method is considered as a renewable way of method. And another things, the importance of this method is for this purpose, the source is water which exists in a large scale in a planet, and the water can be split either. The water splitting can be conducted either by photochemical method or by electrolysis. The photochemical method is considered estimated economically more promising because of the existence of large solar cell, and these are considered that it can replace the fossil fuel because of it is in such a sufficient scale that could replace the fossil fuel, as well as it can meet the rising global energy demand. But we should not forget about the diurnal variation, because the photochemical system will work, it can split the water at daytime, but what about the night? And we don't have such a capability to store all the solar energy. Even though if we store the energy, the density will not be same as we can find during the daytime. But our modern society only believe on continuous supply of the energy that should be provided both day and night. For this purpose, the electrolysis method is more promising as compared to the other, but in electrolysis method there is the problem in the sluggish nature of oxygen evaluation. The hydrogen production is easy, but to evaluate the hydrogen, that process is very slow. For that purpose, we need some of the electrocatalysts which can increase the removal of oxygen and could fastly split the hydrogen, could fastly split the water. For this purpose, we synthesize. There are many reports about the cobalt oxide which work as a best electrocatalyst in water splitting. So what we have done, we made a silica as a porous material which can help in the transportation of the charge, and we prepared the silica and we treated with different temperature, and that's why we treated at 35 degrees centigrade, 100 degrees centigrade, and 130 degrees centigrade. And then we grow the cobalt oxide on the surface of this silica. You can see from the 10 images that the silica which has been treated at 35 degrees centigrade has open network, but the other which is treated at 100 degrees centigrade and 130 has little bit compact structure. When we applied these and we studied the linear voltagram, it is clear from the voltagram that the pure electrode, it shows nothing current density, and we also compared with the commercial cobalt oxide also doesn't show much current density. But when we go for the mesophorous cobalt oxide, it gradually showing the high current density at low over potential. And in the water splitting, the important thing is the low over potential. You have to split the water at low over potential. Among these, the cobalt oxide which is grown on the silica treated at 35 degrees centigrade shows the high current density at low over potential. Then we selected this material and we treated a different pH using different concentration of OH of electrolyte, and we found that when we are increasing the concentration of electrolyte, the current density is increasing and the over potential is reducing, because the OH ion in electrolyte may interfering in this system. That's why it increase the current density. The efficiency of the catalyst is imparted, but on the same time the stability is also an important factor, because different material, different material has been used as electrocatalyst for water splitting, and the well-known material are ruthenium and iridium oxide that can be used as the best electrocatalyst. But the problem of that electrocatalyst is their price, their scarcity, and when you applied the high potential and you check the stability, that is not stable at high potential. But when we applied the high potential 0.8 volt to the material, it for almost 200 minutes it is stable. There is no deactivation in the electrocatalytic property of this material. Then we tried to grow the cobalt oxide on the surface of carbon nanotube, graphene oxide, and graphene. And we designed a material for the water splitting, and when we applied, this is the same images of the material what we grown, and when we applied to the electrochemical property, you can see from the linear sweep ultragram that the cobalt oxide which is grown on the surface of graphene oxide, it shows the high current density and low over potential as compared to the other material. Then in the similar way, we studied the different pH, the effect of OH ion, and it clearly shows that the OH ion is interfering and is showing the high current density when we are increasing the pH of the electrolyte. This, we calculated from the Tafel slope sum of the slope, and it shows this Tafel slope gives the activity of the material. In this case, what we have done about to check the stability, we kept the electrode in the system for a long time, and after several minutes, sometime 10 minutes, sometime 20 minutes, we checked the stability, and we were running the system, and we checked almost 9/10 after each 15 or 20 minutes, it was still stable. So it indicates that the stability is the material is stable for a long time. Then we checked another combination, because there are a lot different literature which shows the nickel and manganese as a good candidate for the water splitting. Then what we have done, we made a combination for cobalt, nickel, and aluminum, and we got, in this case, when we synthesized the material, it was in the form of LDH, and we compared this LDH with the cobalt aluminum nanoparticle and cobalt nickel nanoparticle. When we applied the material, the LDH was showing some sheet-like structure, but the other material was showing the nanoparticle. And when we applied to the water splitting, the LDH was showing high current density even at lower potential. And according to our speculation, that the LDH has layer structure, and inside the layer it was the carbonate ion, and maybe when we use this material as the anodic material, the OH ion is coming because of the layer structure. The layer structure of the LDH has positive charge, and maybe the OH ion is coming very frequently. That's why it is showing maybe more high current density at lower potential. Then we tried to make a cobalt mesophorous material by following some literature. In that case, what they have done, they have made a core shell using the nanomaterial coated with the silica, and then they have coated with the polymer. After that, the silica they have extracted and they have made a core shell. We tried for that one, but we didn't success to, we coated the material cobalt oxide with the silica, but we didn't success to get the polymer chain around this one, around the material. So we tried that why not we should check and compare the result with the previously hard silica template. And when we studied the electrochemical property, we compared this material with different other material like cobalt oxide and co-doped tin oxide and iron, and with different material. But this silica material was showing the high current at low over potential. And this maybe we also in the similar way we studied the pH effect as well as the stability and everything. So this means that maybe the silica, the porous material, help in the transport of the charge carrier, and that's why it shows the high current density. In conclusion, we have designed different material in order to check their role as electrocatalyst for water splitting, and we have found that the cobalt oxide is working very well as electrocatalyst, but you have to designed in a different way. There are several literature, they are showing that if you dope with some other element, it shows the high performance, but we tried to dope with the different material. Till now we didn't get the much achievement, but as the mesoporous material, it shows the high current density at even lower potential. And thank you so much for you.
Thank you, Dr. Sheikh, for this talk, and the gate now is open for any questions or discussions.
Some of the current voltage curves seem to be linear, not exponential. So are you sure you don't have control by serial resistance in solution? You know what I mean? Normally the ID curve must be exponential increase, but
Here maybe in the this one. Yeah, in the graphic.
Not exponential. So this is strange.
This one? Or you are talking about this?
All of them are linear, but they should be like exponential. Only the last one is exponential. This is linear.
Yeah.
So I think you can check by impedance spectroscopy that the serial resistance is not very large.
Yeah.
Because otherwise the resistance, the current, a large current, the current becomes controlled by the serial resistance.
Yeah, but I found something, because when we were performing the experiment, some bubble was creating on that one, and whenever the bubbles create in this system, maybe that was creating resistance, and that mostly we were getting from that purpose, because the bubbles were creating on the electrode surface, and that was maybe causing resistance.
Yeah, so this is a problem, because when you put the Duffel curves, they are not linear, they are like a curve, because it's not
No,
exponential.
but normally in the TOEFL, they have shown that some people, they have shown that it shows the two slopes, not only one slope. The reason is due to this one.
Okay,
Yeah, yeah, inshallah.
Any other questions here? So we go to the ladies or female section. Do you have any question, please? Are you with us? Do you have any questions, please? So I have one question.
Yeah.
Regarding the preparation of cobalt oxide, by which temperature you did the preparation?
No, we just normally keep almost 60 degrees centigrade initially, but in first case we calcined, but most of the just silica we calcined. We are just checking the as grown material, not the calcined material.
Grown by hydrothermal method?
Hydrothermal method, just, yeah. Oh, okay, sir.
So thank you,
Oh,
Dr. for
thank
this lecture.
Thank you.
We'll go to the next talk. Muhammad Riri is here. Dr. Muhammad Riri. If he is not here, we'll shift to the next one. Dr. Muhammad Ramadan Abdul Majid Al-Assar. Dr. Muhammad Ramadan Abdul Majid Al-Assar. We did already the registration. We asked you today. We did registration, so
Maybe they are in the other room. Maybe they don't.
this is room 2. So we have one speaker who wants to switch from to the morning. We can start before going to the last one. So this talk will be given by Dr. Fatih Ayal from Material Science Engineering Laboratory, Algeria, and from Technology Development Division in Algeria also. The title of his presentation is Electrochemical Behavior of the Microstructure
this one?
of
Yeah, this one.
API 110 steel casting pipe in an acidic media with an organic inhibitor. So please.
Bismillah ar-Rahman ar-Rahim. Thank you so much, dear organizer, for allowing me to speak before this afternoon because of a trip to Mecca. Yes. So, I'd like to present a work about electrochemical behavior of an petroleum steel used in casing pipe with acidic media and organic inhibitor. This work was done with inside the Material Science and Engineering Laboratory in Algiers and aided by Technology and Development Division, which is a part of the Algerian petroleum company Sonatrach. The work will be presented as by introduction, motivation, a presentation of studies, experimental study, analysis of results, and a conclusion. Well, I speak about steel, which is in oil industry very much used because essentially of its good mechanical properties. However, this material is attacked by at every stage in the life and of every oil and gas field, and it's subjected to corrosion at any step. So I'd like to show to you here some cracks, some practical case cracks, and they are arriving or occurring in high collapse casing streaks during fracturing operations in shale gas wells. I'd like in this coupled problem of mechanical and chemical to highlight on the effect of microstructure, and we can see here some microstructures where begins and where we can see the initiation of crack and its propagation, which we like to link to the microstructure, the bulk and surface microstructure. So our motivation in this study is to improve the use of this materials behavior in two domains. The first one is the choice of a suitable composition of the steel, and moreover the control of its microstructure. The second one is the selection of a suitable inhibitor according to its interfacial and electrochemical actions, which leads to an acceptable efficiency against corrosion. So in this study, we used a high strength low alloy steel according to American Petroleum Institute normalization, and at different microstructures. The media used was an deaerated saline solution, and the inhibitor, organic inhibitor, was of mixed one at different concentration. The experimental procedure was to carry on some heat treatments leading to different microstructure and to characterize the metallographic situation, and after that to make characterization, electrochemical characterization of the structures by voltammetry, sweep voltammetry, polarization resistance, and impedance spectroscopy. So our material, you can see here, it's chemical composition. We highlight the elements which are in very little concentration, and for these kinds of steels, they are obtained by a thermomechanical process. Here it was thermomechanical rolling followed by rapid cooling, fast cooling. And we have for these structures the elements which are dispersed inside the microstructure, and they lead to very good mechanical properties such as ductility, formability, and weldability. That's for the material about metallurgical composition and mechanical properties. But in fact, we can see the curve at the right. Well, when you are in effective conditions industrial conditions in petroleum media. You have the presence of sodium chloride and dioxide of carbon, which have detrimental effect where they are in specific concentrations to the steel. And especially the corrosion which is caused because of the heterogeneity which is resulting from the different distribution of alloy elements and the internal stresses because of the formation of some non-equilibrium phases. So we made some suitable heat treatments to modify, to have some different microstructures and to characterize them. And these treatments simulate practical cases such as welding, post-welding, post-heating, and also. And the specific heat treatments are the following one. The first one is an homogenization, which gives a ferrite perlite microstructure. The second one is a hardening of the microstructure obtained by quenching and giving a hard phase, which is martensite. And the third one is a softening by tempering this hard phase, which is martensite, which reduces the internal stresses and gives the best mechanical resistance hardness ratio. Here are the different treatments. So you have homogenizing at 950 degrees, quenching after 30 minutes to have this microstructure, which is martensite with the biggest hardness compared to the as received one. And the second type of treatment is an homogenizing longer, which leads to this microstructure, which is a banded structure constituted of ferrite and perlite. And the two last one are an annealing, a tempering of martensite, and then an annealing during two different times, leading to this and this one microstructure, which are more homogeneous and have almost the same hardness as the as received one. Practically the results, I'm sorry, it's not very well, indicates, I can indicate this data, which indicates that the results of voltammetry, by comparison between the as received material and the quenched one, we have a worse behavior for the quenched one, and we have a better one, a better behavior when we make tempering of austenite. I come back here. We can compare the electrochemical, the voltammetric chemical of the hardness of the hard martensite compared with with the treatment of tempering, which gives better behavior by less potential electrical potential, corrosion potential, and less rate of corrosion. That's about voltammetry. Oh, sorry, very sorry for. What we can say that we had in the second time we had put inhibitor on inside the media, and the results summarized are that the inhibitor acts cathodically with the as received structure and the homogeneous one, and acts anodically with the tempered one. That's we can explain that by the mechanism, the interfacial mechanism of the inhibitor onto the surface, which is constituted by different microstructures. The results in impedance indicate in all cases that we have a higher polarization resistance in all the times. That the polarization resistance and also resistance of transfer of charge. We have here presented on the first microstructure all the results of corrosion rate with increasing the inhibitor concentration, the polarization resistance, transfer charge resistance, and ohmic electrolytic resistance, which indicates at each time when we increase the concentration of inhibitor a best resistance. That's for the as received one. For the all microstructures, all to health treatment, we have an effect, a clear effect of the inhibitor concentration. So we have the best results for the higher concentration. We are here. We put the efficiency, which is the ratio between the polarization resistance between the situation without and with inhibitor. And we can see that here all the results indicates a good behavior when we put our inhibitor, and we reach amounts till 80%. When we try to make a link with the metallographic microstructure, here is the microstructure obtained by homogenizing at 950 degrees, and we obtain after 2 hours of treatment such a microstructure constituted of alternate bands of ferrite and perlite. And when we look the application of inhibitor follows the bands. That's because this inhibitor acts with some phases particularly, especially. For the other microstructures which are more homogeneous, we can compare the as received one with the other one, the quenched one, martensite hard structure, and the ferrite perlite structures. Here, the application of inhibitor is the covering is much more on all the surface compared with the homogenized one. So, in conclusion, the main remarks concern the effect of the microstructure to the sensibility to corrosion and to the efficiency in the action of inhibitor. The hard martensite, which is obtained by rapid cooling, is much harder and is less resistant to corrosion inside the media, the acidic media. It's followed by the banded structure obtained by the homogenizing treatment. After quenching, when we carry on a tempering treatment, we obtain a softer structure constituted of ferrite and perlite, and the electrochemical behavior of such microstructure is better than the first one, and is almost the same than the as received one, as received steel of the beginning. About the inhibitor, its efficiency looks important with the hardness structure and at a less degree with the tempered one. About the banded structure, the efficiency of the inhibitor seems to be somewhat less sensible to the inhibitor protection. So the link with the microstructure is that the protection by organic inhibitor is according the adsorption on some specific metallic phases. And these results in summary highlight the importance of the control of microstructures, steel microstructures, in the choice of an efficient inhibitor. That's my.
Thank you. Thank you for your presentation. We have some questions, remarks. In the end section of the next section, we have some questions or remarks, please. If no, so thank you.
Thank you very much.
He's here. Dr. Muhammad Ramadan Abdul Majid Al الصعب. If no, so we'll shift to the last presentation.
Good afternoon. Yeah, okay.
Yeah.
No. His presentation is afternoon. He's asking if he can do it now.
No, because with the time frame, we have only one lecture. Would
Just
as scheduled
try.
with the doctor.
Just try.
Because we asked last presenter, he switched it from afternoon.
Okay.
So we couldn't take two talks. The last talk in this session will be presented by Dr. Wafa Muhammad Morsi Muhammad.
Yes, sir. She is there.
Yeah, she's there? Okay.
Yes, sir. We are.
Okay. Dr. Wafa, she is associate professor at the Building Physics Institute, Housing and Building National Research Center in Doki, Egypt. And her presentation will be entitled Mascot Lead Oxide Particles Characteristics and Analysis.
You are in control now.
So we can start.
Sorry, sir. We will start within 1 minute.
No problem.
Okay.
Quite.
Thank you.
You'll go for it. Let's go
So you can start.
So I try
Thank you.
my.
Today, my talk about beta lead oxide characterization and preparation using in-shell propose. الحقيقة أنا سعيدة جدا في التجمع الكيميائي الهائل الموجود في جامعة الملك عبد العزيز، وأنا فيزيائية وجاية من المركز القومي لبحوث الإسكان والبناء. المركز القومي لبحوث الإسكان والبناء هو قلعة للمهندسين الحقيقة، فيمكن يشرفني جدا ان انا بمثل المركز النهارده في جامعه الملك عبد العزيز في كليه العلوم قسم الكيمياء. Housing and Building National Research Center is one of the most important research centers in Egypt and in Arabic countries in construction field. It has high level of research and industry coordination. It has partnership with local and international universities. Housing and Building Research Center has infrastructure in engineering laboratories, scientific laboratories, computers facility, and many labs. Housing and Building National Research Center has many activities in applied project, in construction codes, in analysis, chemistry and physics, basic research, and has material and control laboratories, structural laboratories, soil mechanics and geotechnical engineering laboratories, processing of raw materials laboratory, acoustic laboratories, thermal insulation and environmental GIS, energy simulation, vibration measurement laboratories. أنا بدأت الحقيقة بالنقطة اللي بتكلم فيها عن المركز عشان أربط علاقة المركز بالساينس، إن مش مجرد مركز القومي لبحوث الإسكان والبناء يبقى انجينيرنج وبعيد تماما عن الساينس. بالعكس، انت عندنا البيزك ريسيرش، عندنا الفاسيلتيز لكل اللابس اللي ممكن نستعملها. الابستراكت بتاع البحث بيتكلم عن بيتا lead oxide powder were prepared by Solgen method in through the reaction of lead acetate solution with acid.
We can see you here.
Okay.
We can see you here, yeah.
Beta lead oxide has many applications in industry and in shielding radiation in the most main this work. Conductive nanocomposite preparation by nanoparticle lead oxide to apply radiation shielding in one of the most main aim of this work. This work aim to radiation shielding. Radiation, many types. It may be electromagnetic waves or nuclear radiation or ionizing radiation. In all cases, it depends on reaction of material with the radiation. So, it's a barrier where the radiation is incident on the material and after that transmitted will reduce. Nanopowder work were characterized by X-ray diffraction, FTIR, thermal gravimetry analysis, and DSCC to study crystallographic thermal stability of the powder. Scanning electron microscope and high-resolution transmission electron microscope and selected area electron diffraction were investigated to study the morphology and structural form of the product. Scientific background of nanomaterials have attracted the attention of researchers not only by their particular physical and chemical properties, but also by their application in various scientific fields. As Dr. Syed Mustafa Syed yesterday talked about nanomaterials, the electronic properties and the electronic motion of the electron start at 10 nanometers. Because, so in nanomaterial, you can reach to specific and unique properties. في الحقيقة أنا دايما بتكلم عليها بقول إنها بتبقى عاملة زي عقلة الأصبع، زي عقلة الأصبع. الماتيريال بتبدأ توصل للإلكترونيك ستراكشر بتاعها، بتنزل لإنك بتوصل للإلكترون موشن، فالإلكترون بيبدأ يتحرك، بيحصل له فايبريشن داخليا، بيحصل له كل التفاعلات اللي ممكن تتخيلها، بيبقى عامل زي عقلة الأصبع. المادة اللي كانت انسوليتد بتصبح كوندكتور، المادة اللي كانت أوبيك ممكن تبقى ترانسبيرنت. كل المواد بتتغير خواصها تماما. Lead oxide are very fascinating because of its numerous phases. Lead oxide has many types and many phases. Lead oxide is an industrial material due to its unique electronic and mechanical and optical properties. Its potential application is in nano devices and in radiation protection and in batteries, X-ray sensing application and in medical applications. Advantage of beta lead oxide because it is a transparent conductor and high dielectric constant. It has a high refractive index material, and both alpha and beta lead oxide are photoactive semiconductor material. Our experimental work depends on another method of depend on Solgen method, which used before in our work and published in Journal of Applied Physics at 2012. Beta lead oxide nanoparticles were prepared by Solgen method. First, certain molarity of solution was prepared by dissolving requested weight of high purity lead acetate with oxalic acid per weight in 100 millimeter of water, distilled water, under magnetic steering for 2 hours. We left the solution about 5 days until viscous white solution is obtained. The obtained solution was held in an oven at 100 degrees centigrade for 8 hours and cooled to 70 degrees centigrade. And still to obtain the gel that was then aged for 18 hours at room temperature. Finally, the gel was calcined at high temperature more than 400 degrees centigrade for 3 hours to have a yellowish green color of beta lead oxide. Characterization systems used in this study: X-ray diffraction with speed rate 2 degrees per minute in the range of 2 theta, start from 5 to 70 degrees. High resolution transmission electron microscope to analyze the shape and the inner structure crystalline size of lead oxide. The surface morphology analyzed by scan electron microscope and operating at 30 kilovoltage and magnification power 13,000. Thermal studies were analyzed by DSC, started from 25 to 650 degree with heating rate 10 degree per minute under nitrogen atmosphere. FETIR used in range 4,000 to 450. XRD study. It is clear from XRD pattern, it is pure beta lead oxide. Diffraction peaks refers to orthorhombic beta lead oxide in a good agreement with the standard peaks position. Due to the annealing temperature was in range 450 degrees centigrade. Also, there is no impurities. Maybe you can see only sharp peaks. In the background, many indications there is no impurities. عايزه اشاور لحضراتكم ان البيكس الشارب دي كلها الشارب دي كلها بيتا ليد اوكسايد اللي هي المسيطات اللي احنا بنشتغل عليه. اما الحاجات الصغيره اللي اوريدي موجوده تحت دي تريسز ما نقدرش نتعامل معاها على انها امبيورتس. It is clear from the sharp and strong peaks it has a good crystallization structure of beta lead oxide. From the data of X-ray diffraction, we used Scherer equation, physical Scherer equation, to calculate the crystal size of the particles, as shown in the figure, in the table. In the table, the crystalline size of beta lead oxide was ranged from 30 to 121 nanometer with an average 83.9 nanometer. The calculated average crystalline size of beta lead oxide is a good agreement with the value reported before. X-ray diffraction data is well consistent with the following data. Thermal gravimetrical and DSC study, as appeared in this curve, show nano lead oxide is stable till 120 degrees centigrade, at which temperature it loses the coordinated water molecules. وفي الحقيقة مع الرغم ان احنا حرقنا annealing of beta lead oxide to 400 degree, but it absorbed some water from the atmosphere. It loses the coordinated water molecules with an endothermic effect about 123 degrees centigrade and the heat enthalpy 0.193. In addition, there are two distinctive endothermic effects at about 275 and 33 degrees centigrade. The obtained TGA and the DSC indicate that our prepared beta lead oxide is more stable than others prepared from lead oxalate, which may be due to higher calcination temperature in the preparation. Thermal analysis, also by thermal gravimetrical analysis at 225 degrees centigrade, occurred with weight loss about 1.447 percentage, which may be ascribed to the composition of lead oxalate. From previous work, this indication by lead oxide because the oxidation number of lead ions is constant during the thermal decomposition process. Lead oxide was formed at temperature as low as 500 degrees centigrade. Surface morphology. Surface morphology starts with scanning electron microscope. Maybe the resolution and efficiency of the microscope, it is not enough high, but we have indication from this image as following. The particle morphology was disordered and the particles were agglomerated in a nano range, about less than 10 micrometers. The morphology of lead oxide powders with salt gel method is uniform as smaller than 10 micrometers. And in the second image, transmission electron microscope confirmed the accumulation of the particles. High resolution depth and selected area electron diffraction pattern of lead oxide nanostructure gives diffraction ring composed of spots suggested that nano-beta lead oxide is a single crystal with average crystal lattice shape of 6.371 nanometer. High resolution transmission electron microscope image of beta lead oxide nanoparticles were investigated to give agreement with X-ray diffraction in this work in the average size and shape. The average lattice distance is about 0.31 nanometer, which are close to interplanar spacing between 1.101 crystal face of beta lead oxide, which confirms the formation of nanostructure. FTIR used before annealing and after annealing. So FTIR is tools to understand the function groups of organic molecules. Infrared spectra of dry gel before drying and drying the powder at 400 degrees centigrade for 2 hours, as shown in this figure. FTIR spectra confirms that there is new peak appears at about 450 in wave number, which is suggested to PBO bond, lead oxide bond. Conclusion: synthesis of beta lead oxide nanocrystalline via salt gel method is a simple and inexpensive and economical, and it may be introduced as reproducible process for large-scale synthesis of lead oxide. X-ray diffraction indicates that the obtained lead oxide was in nano size with orthorhombic lead oxide is high purity. Thermal gravimetry and DSC analysis indicate lead oxide are stable in nano size. The morphology of beta lead oxide powder with salt gel method by scanning electron microscope confirm uniform and smaller than 10 micrometer. Particle will be expected in nano size. The selected area electron diffraction pattern indicates that beta lead oxide nanopowder is a single crystal. High resolution transmission electron microscope image of lead oxide nanoparticle indicates that lead oxide powder consists of nanometric with average particle is about 82 nanometer. Thank you.
Okay, thank you. The gate is open for discussions or questions. Do you have questions here? So in the female section, do you have questions also? In female section, do you have questions? So I have one or two questions. First one regarding the no question. Okay, my question is at the beginning, regarding the preparation method, have you tried, other sources of lead salt, like maybe, you are preparing using the oxalate, you are precipitating the gel as oxalate. Have you tried as any other salt to precipitate it as maybe hydroxide or carbonate to obtain the gel, or by using maybe other method like hydrothermal route?
And another one, please.
Different methods, to obtain or to improve maybe the quality of your product.
Yes. No. I didn't use another method. I used usually salt gel method because it is inexpensive and easy. But your question is very nice to use in the same method with another raw material or source of lead, maybe lead oxide, another one.
Yeah, maybe I can suggest you, to try to use the hydrothermal, to put obtain the gel under hydrothermal conditions. For some time you will.
Maybe give me nice shape.
Yeah.
From my experience, I think hydrothermal gives nice shape of nanomaterials.
Okay, and the second one, in which field you are going to apply or to check the applicability of your obtained material? You are preparing just what?
You asked about lead oxide applications.
Yeah, the application. In which field you want to test it or to apply it or to use it? Maybe you can collaborate with Dr. Nazir Al-Dir or.
Yes.
You asked my question. That was my question. So the purpose.
It's my pleasure to.
You gave a very nice presentation. We really enjoyed seeing your presentation. Now my question is, you have two phases, alpha and beta, but you didn't explain what is alpha and what is beta. That's a different question. But now coming back to the beta lead oxide, are you trying to use this in the paint industry? Because lead has some problems, but anyway, your purpose, is it going to be a pigment for building applications, or what's the purpose of your study? That was my question actually, but you already asked.
Thank you for your question. In the presentation, I talk about beta because I have another applications in alpha beta lead oxide in 2013, as you see here.
Yeah.
There is two phases depend on structure, crystal structure of the lead oxide. Just crystal structure, but it will change the properties.
Thank you.
The second question about the applications. As I talked in the first slide, I talk about applications in shielding, because you can use lead oxide particles in another matrix, in another material, to use in building, in shielding building, in hospital, in concrete, maybe in many nano device, in imaging, in sensing, X-ray sensing. I talk also about applications of lead oxide, but this study already continue till now about applications of lead oxide in shielding.
Thank you.
In shielding properties.
She's from the building station institute, so in her field. So thank you for your presentation again, and by this talk we will reach the end of our session today. Now we have break for pray and lunch also, and we'll start the next session after that. Thank you again.
Thank you.
No, the figures are not coming, completely not visible. On the computer I can see, but there it is not, so that's why I'm changing some slides. On the computer I can see.
Professor, after your lecture, can I use your computer?
Yeah, no problem.
Okay. Because there is problem.
Yeah, but I also have problems already here.
Maybe how much time do
We have to go maybe. I cannot.
No, it's okay.
Some of them are really bad, but it's okay. We can go ahead.
It is my pleasure to introduce Professor Zakiruddin Sheikh Mohammed. He is a senior research scientist and lecturer of chemistry at Laboratory of Photonics, Interface Institute of Chemical Science, Engineering Faculty of Basic Science, École Polytechnique Fédérale de la Saône. He obtained his PhD from Osmania University, Department of Chemistry, India. Professor Zakiruddin is from the highly cited peoples. He published more than 282 papers and more than 20 patents. His citations reaches now about 30,000. He is from top 10 chemist list of, according to Thomson Reuters. He is in the rank of 53 in the chemist list. He from March 2014 he is appointed as a distinguished adjunct professor at KU, Jeddah in Saudi Arabia. I hope we amuse his lectures about the solar cells.
Thank you, Chairman, for your kind introduction. And I would like to thank Professor Abdullah Asri and organizing committee for giving me this opportunity to come over here to present our group's research activities. So today I'm going to present on the recent trends in mesoscopic solar cells. As you know, the global population is increasing day by day, so it is increasing also the energy product demand. So if you look at by 2035, it is going to be almost 40 billion BTU needs to be energy required. So that means it's by 2050, it's almost going to be double the energy which we are using right now. So in the 20th century, most of the energy demands was satisfied with using the fossil fuels and nuclear energy in contributing. But the problem of the fossil fuels is the pollution, and which is releasing the greenhouse gases and is contributing for the global warming. And also, it's not only that the fossil fuels are not renewable energy, so its future is going to be depletion. So one has to find the alternate way to find this fossil fuel energy. And the nuclear energy, another one which we are using, but as we have seen in the Fukushima disaster, it tells us that this is also not the right energy one can use for the future energy demands. So this is shows the increase in the temperature, global warming of how it's changing, and last year was recorded as one of the hottest years on record. So that's why we are trying to find a alternate energy source by using renewable energy, and as you all know that we have the highest energy which is coming to Earth is from the sun, so which is free of cost, and one can use this solar energy to future energy by using the photovoltaics. So in this direction, we are going to work on the licensed solar cell, which is supposed to be the cheap and going to be high performance devices to contribute for the future energy demands. So if you look at the dye-sensitive solar cell, the breakthrough of the dye-sensitive solar cell can by the breakthrough of this applying the mesoscopic TiO2 film. And if you use a single crystal TiO2, you see that the LPC is 0.13% efficiency, whereas if you look at the mesoporous structure, the LPC is more than 80%, which shows the advantages of mesoporous TiO2 film as a substrate for the dye-sensitive solar cells. The main reason for this advantage is increasing the surface area by 10,000 fold when compared to the single crystal. So here are the few of the advantages which we have with the mesoporous structure film, because this also can act as a scaffold to absorb the dye on the surface of the TiO2, and also it for the this is the interconnection of the TiO2 particles makes it collect the back contact to the electrons ejected from the dye-sensitive solar cell. So if you look at the figure here, it's very simple, and in fact, Professor Hackfeld has given a talk yesterday, and then he gave you detail about the principles and basic operating of how these dye-sensitive solar cells are working. And here I will show you briefly those who have not attended that talk to give you an update. So here basically we have two transparent conducting oxide substrate we use. One is as a deposit the TiO2 as a substrate to use as a photoanode, and then the second conducting glass we use as a counter electrode, where we use platinum as a catalyst to reduce the catalytic activity of peroxide. So once the light is absorbed on the photoanode, then the dye goes to the excited state and it injects electrons into the TiO2, and then inject electron percolate to the film and then goes to the back contact, and the oxidized form of the dye, which is regenerated by the electrolyte, and then it's diffuses to the counter electrode to re-reduce the counter electrode. So this is the operating principle of how the dye-sensitive solar cell is working. And if you look at the activity of dye-sensitive solar cell, the first patent application was filed in 1988, and by now I think there are more than 3,000 patents in literature. Shows how the DSC was, people are working on it. This is a slide to show you that the DSC is like a see-through. I mean, one can use this as a transparent photovoltaics, which can be used as building integrated photovoltaics, so that one can replace the glass windows of the buildings with this, so that at the same time you are collecting the electricity to use the household applications. So there is a lot of work, basic research has been done on the DSC. For example, Filippo has worked on the theoretical modeling of this one to show how the dye is absorbed on the TiO2 surface, and then also it shows how the binding coordinated to the TiO2. For example, if you take this N3 dye, where we have the two bipyridine ligands has 2-carboxy, so this has different possible modes which can bind to the surface of TiO2. But the best optimized condition is it's taking 1-carboxy pyridine from each ligand to bind to the surface, which gives you the lowest energy conformation. There also a lot of work has been. This is the one has been done by Munich group here, and they have shown that to go in depth into the integrity of the molecule, how it is absorbed on the surface of TiO2, to show the conformational analysis on the how it is binding in the sub-micron nano levels. And here this is the one, basically as I showed in the earlier slide, how the DSC is working. So it has a competition of different kinetic reactions going on. So here it can briefly explain you what are the kinetic reactions is happening. So once the dyes go to the excited state, it injects electron into the TiO2, which is time scan of 100 femtoseconds time scale. And the injected electron, and also before injecting, the excited dye can also come to the ground state, which has a deactivation period of 50 nanoseconds. So this reaction is competing with this faster reaction of injection. So there is no deactivation process is going on. And the injected electron into TiO2 percolate to the TiO2 nanostructure and then go to the back contact, which is also into the microsecond time scale to millisecond time scale. And then if you look into the injected electron, there are two possibilities one can happen. So you have a redox electrolyte in the system which has an oxidized species, which oxidized species can take the electron from the injected electron into the TiO2, that is called a recombination, or the injected electron in the TiO2 can recombine with the oxidized form of the dye, that can also be a recombination process, which is in the millisecond time scale. But these two reactions are competing with the dye degeneration because it's a very fast reaction where you have this microsecond time scale that is happening. The reduced species of iodide in the redox electrolyte intercept with the oxidized form and it's reduced back. So that's the way it is. No more you will see the oxidized species there. So fortunately, in these competing reactions, all our reactions are favorable. That's why we see that licensed solar cell is working efficiently. So if you can put in on the scale, this looks like that. Electron injection is in this time scale, which is fast. Dye degeneration is here, which is also very fast. And there is only a bottleneck is the electron transport in the TiO2 film and interfacial recombination. So that is the only one problem it can exist, but that can be solved because if you have the thinner films, it cannot compete with this electron transport. It can be reached very fast before the interfacial recombination. So it shows that one can reduce the film thickness to come out of this bottleneck problem there, but to have this one need to have high molar extinction coefficient dyes that gives you the thinner film with no effect on the photovoltaic performance. So that shows the importance of high molar extinction coefficient dyes there. So here you can see that so here is an example of, I'm sorry, here the slides are not properly shown. You can see on the computer, but the visibility is not clear. It is an N3 dye area, which is carboxy-BP, and it is a black dye, which is 3NCS, and then here we have the DX1 dye. It shows the tuning of how the spectral response is, one can tune by changing the geometry around the ruthenium atom. So the main purpose of doing this one is that if you look at the solar snap energy distribution here, the energy spectrum to here is what we have so far is only in the green region the dyes are absorbing. So still we have a lot more to cover in the spectral region to get maximum photon to electricity conversion energy. So that's why the main goal of this, the whole DSC, one can tune the different spectral response on the different dyes, how you can move as far as it goes to the red response. For example, here, this is how from 800 to 1000 nanometers one can tune, and then you can see that how it increases the JSC of the devices. So I'm not going in detail about this ruthenium complexes now. Basically, I will focus on some of the organic free dye sensors, so that's how one can tune the spectral response and what is the role of the substituents, how it plays. For example, here if you can see in this figure, it shows you clearly this is it's well prepared by taking into account that the injection efficiencies are 90%, and then you can see that the absorption spectrum is the x-axis and the power conversion efficiency here. So, and here the difference here is it's plotted with the different colors. This is the energy difference, the loss between the HOMO and the redox electrolyte. So if the loss is 300 millivolts, and then you will have, that is the minimum one can see, you get a higher performance. Whereas if you see, for example, take a N3 and iodide redox electrolyte, the gap between these two is around 750 millivolts. That is the over potential which we are using, because you cannot tune the redox potential of iodide electrolyte. So that is the loss which we lose in the open circuit potential, because the open circuit potential is the energy difference between the Fermi level and the energy of the electrolyte. So if you consider that the loss, if you go on decreasing the loss with the spectral response, so that means you can increase the performance of the devices proportionally. But this is the direction what you can see is with this figure, one can tune the spectral response to the red. At the same time, one has to reduce the gap of this HOMO level and the energy of the redox electrolyte. That can be possible only with the alternate redox couple. So that is the importance of the alternate redox couples comes here for the improving the performance of the ESC. As Anders mentioned yesterday, the use of cobalt electrolytes. Initially, we used cobalt electrolytes with ruthenium complexes, but the success was not good because there is an anic interaction between the oxidized cobalt and the ruthenium. So it's quenching the excited electrons, so that's why we are not much successful with using the ruthenium complexes with the cobalt electrolytes. So that's why in 2010, they found that by designing the donor of the organic dyes such that there will be a bulky group substituted, and then there will be a less interaction of oxidized species reaching to the TiO2. So then you will have less recombination. So from there, it shows how one can use this one electron transfer complexes by using the organic dyes. So here you can see how it affects on the VOC. For example, as I said, you cannot tune the redox energy of the iodide electrolyte because it's a fixed. But whereas in case of cobalt complexes, depending upon the basicity of the ligand, you can tune the energy of these cobalt complexes, and then you can fix at what range you want to have this energy. So depending upon the HOMO level of the depending the HOMO level of the sensitizer, you can tune the energy level wherever you want. So that can contribute for the increasing the performance of the devices. So this is how one can go to the 1 volt of open circuit potential by tuning the right ligands on the cobalt complexes to get the high performance. So now I will move on to how one can tune the spectral properties of the organic dyes. So the organic dyes are divided into mainly two categories. So one is the D-pi dyes, that is donor biconjugation acceptors, and the other one is a donor chromophore and an anchoring group. The difference between these two is families. Here, by increasing the pi bridge, you will create the charge transfer transitions, and then you will get the color here. But here, whereas here in this family, we are selecting a chromophore, which is already a color molecule, and then we are tuning further the spectral properties by substituting the donor with the different donors or with different anchoring groups or the different spaces, how it will affect it. So I will go one by one here. First I will take this D-pi family. So the D-pi family shows that the donor. So in the normally used donors, we have triphenylamines, difluorines, or indolene type of electron donating molecules, which is substituted here. And then you have different pi conjugation systems. One can use thiophenes, EDOTs, or fused thiophenes, because these are the molecules which are heavily used in OPV, where you can have this planar structure here, which is more facilitate the charge transition from donor to acceptors. And then on the anchoring side, these are the two different anchoring people have mostly used. One is the cyanoacrylic acid, which is the carboxyl group, which can be bind to the surface of the TF. Here I will show you an example how you can tune the spectral properties and then how these spectral properties affects on the photovoltaic performance. For example, if you take this molecule here, which is G188, and then it has a E dot molecule here, and then you are making another E dot substitution and by conjugation to make it 2, 3, 4. So they're extending with the E dot, 2 E dots here, and then here, going from here to here, you are adding one more CPDT to this E dot molecule, and then you are adding 2 E dot daughters and having one more CPDT here. So now we can see how the structural variations will change on the photophysical properties of these molecules, and at the same time how they affect on the photovoltaic performance. So to understand this, the electrochemical properties are measured, and then here is tabulated. Here you can see that we have different absorption spectra. So without only one E dot molecule, you can see here it's 580 nanometers. By adding one more E dot, it is shifted at 50 nanometers to the red, which is 533. But instead of another E dot, if you substitute with CPDT molecule, the absorption spectra is moved from 580 to 581. There is a huge shift because the CPDT has more pi conjugation than E dot here. But if you take 2 E dot molecules and then put the CPDT there, it is further shifted to 612 nanometers. So this shows how one can tune the spectral response from 518 to 612 nanometers. It also affects on the molar extinction coefficient because you are increasing the pi conjugation, it also increasing your molar extinction coefficient of the molecules. But at the same time, you also see that there is also an effect on the HOMO level of these molecules. So by increasing this pi conjugation, you decrease the HOMO level, and by having this 270 here, it is close to 0.6 volts, which is very close to the energy of the cobalt electrolyte which we normally use. So that means one has to be careful to see how this dye regeneration will affect there or not. If you look into this is the spectral response, you can see the figure which was tabulated, and then if you draw a diagram with the energy levels, so these two molecules, 270 and the energy of the cobalt Vp, they are very close. It's only 60 millivolts difference between these two. So this is what we have to see whether there is any difference in the PV or not. The photovoltaic performance of these molecules are tabulated here, and then you can see the IV curves and the IPCE. So as expected, in case of 188 to 234, you see an increase of around 1 milliamp current density here, because that can be explained. You have shifted 50 nanometers in the spectral response. So more shift into the red, you will get more current. But this is by sacrificing around 100 millivolts open circuit potential. So this is one has to see why the open circuit potential is gone to 100 millivolts when compared to increasing the JSC. So the overall performance is lower than without substitution. So this, I will come back to this point later. So and first, if you can see this 268, which has 80 nanometers redshift in the absorption spectra, has the highest current. It's around 16 milliamps, and then there is very small drop in the VOC, and then that gives you the highest performance, more than 9%. As expected in case of this one, as we have seen, there is a small difference in the HOMO level and the energy of the electrolyte. It could have been hampered the dye regeneration. In fact, that's what we see, that we see only 5 milliamps of current, and then also low potential there, which is resulting into just a 2% efficiency. So to analyze these differences, we also have done transient measurements, and then we came to know that in case of one E dot, it is so happening that the conduction band shift is moving down because of the dipole of the molecule, which is contributing for the lower VOC. Whereas in case of 268, even though there is a small shift there, but a huge increase in the current density is compensating the performance. So that's why still it is highest when compared to the unsubstituted. So this shows that by tuning a systematic, one can find out the right suitable pi conjugated system to have the high performance. And now here you can see that when you are extending the pi conjugation, for example, why only d pi a dice? Why not DA pi a dice? Donor, acceptor, pi conjugation and acceptor. So what is the difference between DA pi a and d pi a dice? So by substituting a electron acceptor next to the donor molecule, whether it will affect any on the spectral properties or whether it will affect on the photovoltaic performance or not. So that is interesting to see, because by inserting here, this one has an influence or not. So here the structures are, the color you can't see much. This is a diazole, this is the benzothiazole, this is the benzoxidole, and this is the phenoxylene. So by taking this electron acceptor units there in place of this auxiliary acceptor next to the donor, and then you can see how system, this is the without any substitution, and this is blue is the benzothiazole, and then this is the benzoxidole, and then this is the benzopyrene, this is the phenoxylene. So by increasing the pi acceptor level, you see the spectral shift is going to the red. So it shows that you are increasing the spectral response by having this pi accelerated ligand. It's not only that, if you look into the calculations, it shows that there is a good overlap between this acceptor unit, so that makes it, in fact, not only the red shift, it also introduces another charge transition at 400 nanometers, which is helping to have a broad spectral response. So this is how having a DA by a dye can insert another pi charge transfer transition to absorb more into the red. So here another family, what I want to say is, in case of d pi AA architecture, this is just I'm going through some few molecules of what is the difference you see by tuning the acceptor or conjugation, and how this is going to influence on the spectral properties and the device performance. So here by having a benzothiazole next to the anchoring group, or a benzothiazole having a phenyl in between these two, what makes it different? If you look at the spectral properties, and this is the molecule which has a benzothiazole attached directly to the carboxyl group. But by having a phenyl group in between these two, it blue shifts the spectral response. In fact, that's not we want, but what happening is by having a phenyl group in between the acceptor and the anchoring group, it blue shifts the spectral response, and then you expect that this molecule should give you the highest performance when compared to this molecule, because the spectral response is blue. But in practice, when you measure the photovoltaic parameters, you see it's a huge difference between these two molecules. This is the performance of the IV curve without a phenyl group in between the benzothiazole, that is the dye 1, and this is the dye 2, you get the maximum efficiency. So the difference between these two is 1.2 and 8.2. So there is a huge difference. Even though you have a blue shift in the spectral response, you have a higher performance with higher DSC, which is 18.5. So how you can explain that? So to know the difference between these two molecules, the influence of the phenyl group, did some theoretical calculations to show what is happening in the dication stage. For example, by having a dication, that means when the dye goes to the injected into the TiO2, it forms a dication. If you check the structure of the dication, it shows that the dye one has a planar structure, whereas the phenyl one, because of the phenyl, it is tilted. So that's why what's happening is when you have this planar structure, so it is going into the, injecting into the TiO2. At the same time, what's happening is the injected electron is recombining with the oxidized dye very easily, whereas in case of this phenyl group, it is tilting and like a locker. It is blocking the reverse electrons. So that is the main reason why having a phenyl has such a dramatic effect. So if you do this transient experiment here to monitor the laser photolysis, really what is happening, whether there is a recombination there or not. So what we have done is, here we excited the dye, absorb the dye on the TiO2, and then excited it to the excited state, inject electron, and then you monitor the oxidized form of the dye, how it is decaying. One is in presence of the electrolyte and one is in the absence of the electrolyte. So in the absence of the electrolyte, what happens is the injected electron is recombined with the oxidized form of the dye, and then it takes a long time. For example, for dye 2, the injected electron to recombine with the oxidized dye is taking long time. Whereas in case of dye 1, so immediately it disappears. So that means as soon as it injects the electron, the positive charge on the dye is also disappearing. So it shows that the faster kinetics of the recombination. So there is a hugely small difference between the redox electrolyte and without redox electrolyte. You hardly see a difference in these two blue curves. Whereas in case of dye 2, there is a huge difference here in presence of redox electrolyte in the absence of redox electrolyte. So this confirms that having a phenyl is an advantage to have this next to the benzothiazide except where it is close to the anchoring. So these are the few things one can understand how the molecular changes affect on the photophysical properties and device performance. When you go to this donor chromophore anchor system, so here now we will see a couple of examples how it is going to affect. So now we will take this photosynthesis as a source of inspiration when we have a chlorophyll there. So we started working with porphyrins by introducing a donor and acceptor fragments to tune the spectral properties, to create a directionality in the molecule to increase the performance. So first by using this molecule, we obtained with this 12% efficiency. And this morning also, as Professor Nazir also he mentioned in the first slide, the importance of benzothiazide there. I will come back to that slide next. And also the importance of this alkoxy chains in the meso position of 2,6, why they are so important. So here we compare that having a tertiary butyl group in the meta position and in ortho position having a butoxy chains, how they will affect on the photovoltaic performance. By having these bulky groups here, it is increasing the VOC. For example, YD2OC8 molecule here is 965, and here we have 825. So the main gain in this, having this just a simple, the whole structure is same, only this position is replaced from meta position to the oxo. It gives you a boost of more than 140 millivolts. So this is because you are retarding the recombination by having this longer alkyl chains there, where these chains are wrapping up like protecting the TiO2, reaching the cobalt-3 to the surface where the recombination is reduced. So this is confirmed with electron lifetime. If you measure this one, so here in the red one is the YD2OC8 with bulky group substitution. So you can see that we have a higher electron lifetime when compared to the other molecules, which is in agreement with what we have seen the higher VOC. And now we are putting together the organic dye with this one, the porphyrins, introducing the benzothiazole there, which can also gives you the added up the performance what we have seen organic dyes. For example, here you can see the broadness of the spectral shift and then the shift in the absorption spectra. It's contributed to higher performance reaching up to 13% with this one. So the main IPCA, if you can see, without the benzothiazole, you have a value here which is covered with this new transition which is arising by introducing this benzothiazole in the spacer. So this is a different comparison of photovoltaic performance between these two molecules. So now then I can also show you another molecule which is a DPP family, which is also comes under the same, like a chromophore tuning, by using a symmetric and asymmetric, how it will affect on the performance. By taking the symmetric substitution on the DPP, you will see the performance is low, whereas you take the asymmetric one, the performance is high, even though you see the spectral response is blue shifted. So why it is performance is higher when it's blue shifted is, in case of the symmetric molecule, we have more diaggregation, which is causing for the quenching, then you will have less electron density. So that's why even though the spectral response is blue shifted in the symmetric one, you get a higher performance. So because of this experience, what we have done is we tune a little bit on the different donors here. So the same, you have substitution here up to only the donor part we are changing, having as the experience of this cobalt complex, the bulky the donor, we have less recombination, less VOC, and then here you will see that increasing the photovoltaic performance by increasing this donor, you will get up to more than 10% efficiency. So after this, I will quickly show you a couple of slides. As Anders mentioned, that use of copper complexes as a new generation to show high performance, how one can tune the VOC, and also to use a solid cold transport as copper complexes. And in addition to that, I want to show you that recently there is a publication which people have mentioned that it is iron sensitizers, which shows 90% yield. One can increase the, when compared to the terpyridine, this is a remarkable increase in the injection yields. So they are using this type of ligands, they are stabilizing the metal centers to increase the yields of this molecule. So there is a future there, one can work more on, because the iron sensitizers are cheap, to see how it will evolve. And Peng Wang is also working on this different perlin type of dyes using the donor acceptor concept, and he reached up to 13% efficiency by using this type of dyes. And also this is another combination of co-sensitization they obtained using mainly this is trimethylsilane as a anchoring group, which can increases the binding constant, and also it reduces the recombination to get the high performance in combination with like 4 dye. They reached over 14% efficiency. And this is just a comparison of low light intensity, how this DSC supersedes the silicon cells. And then I will show you a few slides where one can use this DSC as a panels in the different people who are using Fujikura has this product applications, and then they also did the testing of the model with all the conditions, and this is the Congress Center of Lausanne where you have this DSC panels there. And G2E is another Swiss company which is producing the modules by using DSC. And these are some low-light applications where you can use for the battery chargers and other stuff. And these are the companies who are involved in DSC. And this is the Milano Expo where the DSC has been shown in this expo. I think I will skip on the next couple of slides and go directly to thank the funding agency and my collaborators, all the people who worked on this project. And thank you very much.
Thank you, Dr. Professor Zakir, and we only have 2 questions for the discussions because of time. Anyone want questions? Yes, thank you. Now we will hear to the lectures by Professors Hosnu Jernuki, Associate Professors from Turkey. The name of lectures is Corrosion Inhibitions, Effect of 8-hydroxyquinoline as a corrosion inhibitors for copper in 0.1 molar hydrochloric acid.
Thank you so much. No, it's working. Yeah. It will be fast.
You have 2 minutes.
Yeah?
You have 2 minutes.
Okay, 20 is too much. So it will be good for Professor Mohammed and Professor Rada, especially because for future corporations it will make a good idea. And welcome. And this work is cooperated with Poland, Gdańsk University of Technology, and Bursa Technic, and also our university. And as you know that corrosion can be defined as degradation of the material due to a reaction with its environment. It's basic. But we know that all metals, except several metals, all are corroded very easily. So we have to care about to protect our metals from different type of environments. So I make a small parenthesis to make the consequence of the corrosion. And we know that due to the formation of the corrosion over the efficiency of the mechanical gas loss, also failure due to corrosion. Especially I will focus on failure due to corrosion and the product gas contaminated due to corrosion and the toxic effect of the corrosion. It's very harmful for people. We know that it's very common in this time Alzheimer's. Why it occurs? We know that it's because of the aluminium. We are drinking too much cans which are produced from aluminium, and also beer, also some cokes, and when you drink this type of drinks and you took aluminium, and this makes Alzheimer's. So it's interesting, and we have to focus on to stop the corrosion. So I told you before that I will focus on failure rule, the domains of corrosion effect. Look here, number of the accidents due to corrosion is the most to compare others, and also number of the accidents by percent, and also the cost of corrosion. Also, you can see it's nearly $18 million. Yeah, so it's quite old data, but I think it's the new data are bigger than this. So that's just a view about the impact of the corrosion. So we know the problem, we know how the corrosion is very important for industry and for healthy and other indirect effect of the corrosion. Because we know that thank you so much. Okay. We know that indirect cost of corrosion is more effective on environment and also in industry. Okay, what's our aim? Our aim is basically investigation effect of 8-hydroxyquinoline on the corrosion of copper in hydrochloric acid with using electrochemical methods. Why copper? It's very simple. question, and answer is also simple, because we use copper in construction industry, telecommunication, automotive, mechanical engineering, and especially heating. And we use copper alloys in heating, copper, brass, all type of copper alloys. We are using heat exchange and cooling system. So when we use this metal in cooling system or heating system, and because of the water, it became dirty or something, there is calcium carbonate or other type of some compounds, and it make corrosion, also some dust around the pipe. So we need to clean this heating system by a solution. So the most common solution was 0.1 molar hydrochloric acid. But it's a good idea to use inhibitor. Why? Because as we know that one of the best important method in corrosion protection is inhibitors. And so we use these inhibitors. You know that there are different types of inhibitors. We use them to stop down the corrosion or slow down the corrosion rate. So we use organic, inorganic, anticathodic, and different type of inhibitors for to get this aid. Okay, and interesting for you, why where we use inhibitors? When we look at this diagram, from petrol refinery, you can see too much corrosion inhibitors they are using, and also petroleum storage and transport. You can see drilling. Also, you can see paper everywhere. In, for example, iron and steel, they are using for pigment acids and other materials, additions of petroleum products. We use lots of nearly $1.1 million cost for corrosion inhibitors. We really, for example, in geothermal corrosion, now we are working on geothermal corrosion, the amount of money you cannot believe too much. They have to use it because they are earning money from the geothermal corrosion by heating houses and factories, and they have to use it. If they don't use the old equipment, will damage in a very short time. Okay, so but for us, green corrosion inhibitors are very important because there is, for example, benzotriazole, as a professor just spoke about. It's corrosive. It's a very good corrosion inhibitor, but also it is not good for health. Also, there are some amine derivates and also some sulfur derivates, phosphor derivates. They are too much, but they are not good for health, especially in the cooling and other closed system. If something damaged, so it's easily evaporated, so it's not good for our lungs and also for health. Yeah? So we are trying to find green corrosion, ecological. It can be from plants. It can be just from date palm juice. For example, we have a work. It is published in American Chemical Society journal. It is we investigate date palm juice as a corrosion, and it works for aluminum. It's interesting. So we are working for green corrosion. But copper is something different. Copper is you know that it's occur copper oxide on the surface, so it protects himself from environment. But by the way, by the time it's corroded again. So we use some inhibitors. One of them are 8-hydroxyquinone. 8-hydroxyquinone from the literature we know it's good for aluminium, but we just check for if it is work for copper, and quinoline derives from the plants, but we have to know that if you use too much, it's not good for health. So you have to use less. So you will see that we use very, very small amounts to see how it's work or not. Okay, so we use copper, and this is our environment. We use 1, 2, 3, 4 concentration of 8-hydroxyquinone. First, we perform our experiment this, and then this, and 4 different environments. So our reference and how to prepare the sample before experiment is written here. You can read from abstract, yeah. And then we perform 1, 2 electrochemical measurement, and also this is third. This is third. This is our method. Just it's patented by us, and there is only 2 universities can make, 2 laboratories can perform this method. And now I will focus on the advantage of this method if you compare to others. Okay, dynamic electroimpedance spectroscopy, investigative system, and you connect the galvanoscope, and this is a digital analog card which is produced by National Instrument. This is the code of card, and we use ZSync, LabVIEW program to measure all. Yeah, we just handmade program. Yeah. And the differences between DEAs to compare electroimpedance spectroscopy, we use very small frequencies, but we use also short time Fourier transform. You know, FTR, you know, Fourier transform formulas. We use these formulas to calculate. For example, in a 1 hour, we took 100 spectrum. So you can understand what is going on in dynamic conditions. For example, we can put this method as a sample, as a small cell, to the airplane or to a tank or a car. If this part is corroded, lamp will open. Okay, change me. Yeah? Just we are trying to do this, and we are in a good way. Okay, let me show you the result. This is classic method, topple polarization result. It's a very good method to understand how your inhibitor is worked. Yeah, it's a potential to logarithmic current diagram, and you can see this is non-inhibitor, and when you add the inhibitor with the concentration increase, you can see it's going to cathodic part. So it is easily, you can say that it's cathodic. But by the way, you can see the anodic branch. The anodic branch is nearly constant, but beta C, the aim, the slope of the cathodic part is here. You can see it's going down. So it's improved us that it is not mixed type inhibitor, it is cathodic inhibitor. The potential also going down to the cathodic part. And when you look to inhibitor efficiency, yeah, if Professor, if it is big, when you add inhibitor is going down, and you can see this value give us information how your inhibitor is working. Look, no inhibitor 63. Now you have 16, 15. So your inhibitor work is protect your sample nearly 80%. When you add 0.016, your inhibitor works. This is obtained from topple polarization. So we perform different methods. Because sometimes one method say good, something you cannot understand. But this is electroimpedance. This is also classical. One of all laboratories can perform this. We can see this is a logarithm of the impedance. I'm so sorry, it's here. You can see nearly 3,000, and when you will look here, and without inhibitor is, for example, nearly 2.3 or like that. And this is theta. The meaning of this is theta. If it is, for example, if you have a sample, you paint. Okay, theta you took 90. Okay, if you paint, so no corrosion, so it is 90. So you can see that maximum inhibitor theta degree is at about 45, and without inhibitor, nearly 30. So it's going
التحية. في البداية نود أن نشكر الملك عبد العزيز وكلية العلوم قسم الكيمياء على استضافتنا لهذا المؤتمر. مؤتمر الكيمياء الأول في جامعة الملك عبد العزيز، ونشكر جامعة الملك عبد العزيز على هذا المجهود الرائع في المؤتمر، للإضافة العلمية اللي أضافتها لينا، بإضافة معرفة جديدة في مجالات الكيمياء المختلفة وخاصة الكيمياء التطبيقية والتكنولوجيا. المرة الثانية بنود إن احنا نشكر جامعة الملك عبد العزيز وكلية العلوم قسم الكيمياء خاصة
we have 60,000 seconds. You can measure 2 days, 3 days, and at that time you can see how the inhibitor acts. Okay, this is charge transfer. Okay, really fast. We have a study. It's about acid rains. Yeah, we put aluminium and we drop acid on the aluminium and we perform how the aluminium oxide when occur. Because aluminium oxide occur very fast. Yeah? Just at that time, for example, when the corrosion happens, going down. Okay, then aluminum oxide occur and then going down. So this is surface heterogeneity. You can see by the time it's still going. So 8-hydroxyquinone for 15 hours we perform, and you can see that there is no corrosion on the surface and still rise up the charge. Okay. Boom. Okay, just accomplished. Okay, this is look just lecture for Professor Rada and so for new opportunity for the new science. Look, this is the AS result. This is you have 100 spectra here, and here the charge transfer is 300, and here you have charge transfer nearly. If you make this circuit, you have nearly 12,000, yeah? Just like this. Okay, so the advantage of theirs, you can take knowledge every time. Yeah? So other methods, you just perform and you can take data. But dynamic electroimpedance, for example, you can take 5 hours, 10 hours, 15 hours. What change? You can see the change. Yeah? When the inhibitor will lose his efficiency. When you have to add inhibitor again, because there are in factories in cooling system they are using inhibitors, and they don't know when they will add again inhibitor. But this system, when the inhibitor loses the efficiency, the lamp or just burning, so you have to change the you have to add inhibitor. Okay, conclusion. Okay, all studies clearly show that 8-hydroxyquinone inhibits the corrosion of copper in 0.1 molar hydrochloric acid, and the results from theirs studies were good in agreement. That is good. So also we have SAM and EDS results. The comparison of these techniques was demonstrated to be a powerful corrosion process. Yeah. For to understand corrosion, I think. For example, in some papers we are reading 1 hour later I perform and I thought, no, I don't believe. Just you have to check in a long time and just to see what's going on. And the polarization measurements demonstrate that act as cathodic inhibitors, and this scientific work indicates again there's an effective measure for understanding of corrosion phenomena of non-stationary systems. Yeah. And moreover, this paper has proved that theirs could be successfully used for assessing corrosion inhibitor performance, and theirs method should be used before every experiment. From before Tafel, from theirs to take knowledge about the system. Reference is project which we took from the university, thanks to Professor Darowiecki and Paul Ślepski from Poland. Thank you so much.
Thank you very much. And we have now open the discussions.
بتقلل مرتبة 36 على لاين
I have one small question.
Yes,
Thank you. Just now you use from your chart use towers with 99%.
Yes.
Is this what is used in the industry?
Yes, it's used. It's used.
We use
Yeah.
towers or
No, just they are using it. 99% of copper they are using it. Because in cooling system, for example, they use brass. But in some places, for example, in the boilers, they are using this.
Nice. Another question is, your new systems that monitoring the corrosions and can I use it? You use it as I see from Richard's on small electrodes in the laboratory. Can you use it online?
Yeah, of course. You can put the cell and through mobile telephone you can check. Yeah, I can show you.
Yes, thank you, Dr. No.
It's nice and smart system.
Thank you.
Good luck.
Thank you.